lecture today by Elia Fioravanti.
Okay, very good. First of all, I need to apologize because I've committed something terrible. It's been pointed out to me that in my first lecture, I said that the existence of non-principal ultrafilter was equivalent to the axiom of choice. It's apparently strictly weaker. So sorry. I hope you can forgive me. Okay. Secondly, so today I don't want to talk about actual median spaces. What I want to talk about is cube complexes, like all the cool kids. So yeah, and I'll try to convince you that somehow, even if you just don't care about ultrafilters, you don't care about median spaces, you don't care about property T, the Haagerup property, you just only ever care about Casio cube complexes, you might still need to use some median algebra techniques, and they can be useful, okay? So that's what I want to do today. Let me just mention that there are a lot of things about median spaces that I would have liked to say, and I haven't, right? I tried to give an overview of all the various sides, right? Like what you can do with infinite dimensional ones, if you care about property T and the Haagerup property, what you can do with like finite dimensional ones, but there are a lot of other nice results. And in particular, like there are two results that I want to mention without writing anything. So Big Badr and Thaler, they proved that any amenable group acting on a median algebra, as long as it's like a compact median algebra with some topology and some weak local convexity condition, any amenable group will always have a fixed point, or rather fixed cube. So that's a strong property that can be used for a number of things. And also Little Badr and Near have some other like higher notions of medians, like of median spaces, where you can, instead of looking at triple of points and the geodesics connecting them, you can look at quadruple of points and like disks filling the triangles, and they also intersect in something small, like a point or a segment, and they show that, for instance, two-dimensional cell complexes, Kazhdan cell complexes will satisfy this. So, okay, but today, again, cube complexes. So let me begin with a definition. Let's start slow. So this has been said many, many times, but so a group is cocompactly cubulated if it acts properly and cocompactly on a cube complex, right? So if it acts properly discontinuously and cocompactly on a Kazhdan cube complex, preserving the cell structure. Okay, so here's the theorem that I want to prove today, and maybe you can just like see it as an example of how sometimes you actually need median algebras. And maybe there is a proof of this that doesn't use median algebras in any way, but I don't know it. If you can think of one, let me know. Theorem, say that G is cocompactly cubulated, and say that H is a finitely generated subgroup. Then you can look at the centralizer of H in G. And what I claim is that this centralizer is itself cocompactly cubulated. Simple enough statement, but this can get tricky, and I'll explain why this can get tricky in a moment. Just a corollary that one gets from this it's the following. So say that a product of two groups is cocompactly cubulated. Okay, right? What we would like to deduce is that the groups themselves are cocompactly cubulated. This is false. I will give you an example. But if one of the two has finite center, it's true of the other one. So if G1 has finite center, then G2 is cocompactly cubulated. Okay, it's clear, right, that the first theorem implies the second, because then you can just take the centralizer of G1, and that's going to be G2 cross the center of G1, which is finite. So you get that. Okay, maybe some things. So there is a version of this by Kropp-Holler and O'Donnell with some additional assumptions on the group. And the theorem, and I mean, the argument I'm going to give for the theorem and the corollary appears in a paper I have with Ivan Levkovitz and Micha Segiv. But yes, if you find a different proof, let me know. Okay, so what's the example? So the example is the 333 Coxeter group, right? So so let W be the 333 Coxeter group. So it's, well, just the A2 tilde tiling of the hyperbolic plane that Thomas has drawn very proficiently a few times. I think I'm not going to be able to do it so well, but I mean this thing, okay. Take reflections. I mean, these are meant to be lines, and yeah. Okay, so if W is this guy, then it's not hard to see that, well, W is not cocompactly cubulated, right? So in particular, this follows from a result of Mark, but in this low dimensional case, you can probably like really just do it by hand, because, well, if W were cocompactly cubulated, first of all, you can construct then a geometric action really on the standard tiling of R2, just because in any cocompact cubulation, the K0 flat torus theorem is going to give you really a K0 two-dimensional flat. And in there, you can see how it intersects the hyperplanes, and you must see exactly two parallelism classes of line. And so you can then, because the action is cocompact, right? You cannot see too many. And then you can just like recubulate based on that space with walls that you have on R2, and you really need to get R2 with an action of the Coxeter group. And this guy cannot act properly and cocompactly on the standard tiling of R2 because it has order 3 elements. So there are no order 3 elements in the automorphism group of the standard tiling of R2, so those will have to go to 0. And the normal closure of an element of order 3 is actually the whole group, or at least finite index. I mean, in any case, it will force you to not be cocompactly cubulated. But, okay, you can show by hand, this is a nice exercise, that if you stabilize, then it becomes, then it acts on R3 actually. Sort of acts on the standard tiling of R3, third cubical tiling, properly and cocompactly. Questions?
What it has?
Sorry?
You said if you sympathetize, then it starts acting cocompactly.
Oh, if you stabilize, if you take a product with Z to the N, right? So this theorem also tells you that if a product is cocompactly cubulated, then the first guy cross some free abelian group is going to be cocompactly cubulated. But then you cannot go back. Okay. So how are we going to prove the theorem? And I want to give 2 definitions that somehow are useful beyond what I'm going to tell you about today, but we're going to use them. So you say that you have just any group acting on a K0 cube complex, and say that you have some subgroup H. Then we say that H, or at least I say that H is a convex cocompact. I'm going to re-describe this in words that are better known, I think, to people. So H is convex cocompact if it acts cocompactly on some convex subcomplex of X. And I'm going to say that H is median cocompact, and you can imagine what comes next. If H acts cocompactly on a median subalgebra of the 0 skeleton. Okay, so cocompactly here just means cofinitely, because the 0 skeleton is discrete, but I write cocompactly to just keep the same terminology. And here I'm speaking of subcomplexes, but if you instead said, a convex subset of the 0 skeleton for the median algebra structure, it would be exactly the same thing. Okay, so the first notion, right, is something that we've seen already in Nier's talk, right? It's the same as saying, well, H corresponds to some cube complex that is locally isometrically embedded in the quotient for the K0 metric. So remark. So if G acting on X is free. I wonder if I'm thinking usually of geometric actions, but I think this should be enough. Yeah, let's say that this is enough. Okay, so if this is free, then convex cocompact subgroups are exactly those that are represented by a locally isometric immersion, sort of, let's call it Q, of some finite Casio cube complex. Because, well, if you have the convex subcomplex, you just take the quotient. That's exactly what that thing. And if you have this, you just lift to the universal cover and you get the convex subcomplex. Okay. Some other remarks. So why do I care about these notions to prove that? Well, so clearly convex cocompact is the strongest here. So convex cocompact implies median cocompact. But if you're median cocompact, right? We've seen a theorem a couple of times ago where, so if you have a discrete median algebra, that's canonically isomorphic to the zero skeleton of a cube complex. So if you act cocompactly on a median subalgebra, you will get, well, this median subalgebra will have, it will be isomorphic to the zero skeleton of some Casio cube complex that will inherit an action of the group. And so in particular, you get a cocompact cubulation. And this cube complex that you get is not necessarily a subcomplex of the one G is acting on. It's just some other thing that you get out of it. So median cocompact in particular implies cocompactly cubulated. So what we're going to show here is actually that centralizers of finitely generated things are always median cocompact. But what is not true is that they're convex cocompact. In general, they will not be. And so here's another example. So consider just a virtually abelian group, namely Z to the N semi-direct product with the symmetric group, where this simply acts by permuting the standard basis elements. So if you look at the centralizer of this finite subgroup, this is not convex cocompact in any cubulation. But of course, it will be median cocompact in all of them. So why is that example true? Well, the reason is that, so when this virtual abelian group acts on a cube complex, you can imagine that it's going to act on some flat, basically. And when it acts on a flat, there will be exactly n lines in Zn that correspond to the convex directions, to the convex cocompact infinite cyclic subgroups. And those need to be permuted by this group. But, so this group acting on lines in Zn has, every orbit has exactly n elements, or sorry, at least n elements. Yeah, every orbit has at least n elements except for the line where all the coordinates are equal. That corresponds precisely to the centralizer. So we cannot have this convex cocompact because otherwise there's either only one convex cocompact direction or there are at least n+1, which is not possible. Okay, so let's prove the theorem. So here's a lemma. Whether you have a proper cocompact action on a cube complex, and say that you have a base point, right? And say that you have a subgroup. Then, so these two properties can be phrased just in terms of the metric, namely, H is well, convex cocompact if and only if the set of median points in the orbit of P stays close. Compact. So take median of the orbit and the orbit point in one point in the cube complex. And this is contained in a neighborhood of the orbit. R. And right, this is like when you define complex, but in a course, then and the similar for median. Okay, so how do you prove this? So one arrow in each of the two statements is clear, which is this, right? So because, well, so G is quasi-symmetric on the cube complex via orbit maps by Min-Schwarz, and then, well, H stabilizes some subset that is actually closed under this kind of operation. And so, yeah, like an orbit is coarsely the whole thing there. So this is going to be, yeah, coarsely closed under the operation. Going back. So this follows from a result of Bowditch. So say that actually M is any median algebra and A is a subset. There is a way in which you can describe the convex hull of something or the median subalgebra generated by something. And it's as follows. So, well, you start doing this and repeating this procedure until you stabilize. So, so let me define curly M of A, which is just a set of medians of all, of any triple of points in A. And curly C of A is essentially the union of all intervals with endpoints in A. And then you iterate. So let's say M to the n plus 1 inductively is M of M n of A, and similarly with Cn. Okay. So clearly, if you do this infinitely many times, here you get a median algebra, median subalgebra, and here you get a convex subset. But what Bowditch tells you is that if you're in a finite rank median algebra, then you only have to do it as many times as the rank. In fact, actually fewer, but at most as many times as the rank. So Bowditch tells you that if the rank of M is at most R, then for every subset A, it's an infinite subset in general, it doesn't matter, right? For any subset, MR is a subalgebra, and CR is convex. Where does it? We're not using cocompactness here. Yeah, I mean, we use cocompactness here because we wanted, we wanted the action of H on the convex subset slash median subalgebra to be a quasi-isometry. Like, yeah, like you really still need to cocompactness, right? Because like you want to say, like when you do this, this is gonna fill out the whole convex set. You need to say that this is close to an orbit in order to conclude this, right? So this arrow uses cocompactness. And we're gonna use cocompactness also going back, but we haven't yet. So, but this part here only uses finite dimension. That's right. Yeah. Here is just if the rank of the median algebra that I'm discussing here is at most R, then this. Of course, now we're going to apply it with M being the zero skeleton of X, so it's just going to be the dimension of the cube complex, which is finite because it has a cocompact action. And I think, so for convexity, to be honest, Haglund did something very similar to this. So I should say this is also due to him. Okay, so now we just do this, right? So say that now, so let's close this parenthesis, this aside on subalgebras and on abstract median algebras. So now just take an orbit inside the cube complex. Actually, let's just call curly O the H orbit of P, right? Well, so what do we know? So we know, right, depending on the statement there, we're proving this arrow. So we know that this curly M of the orbit is contained in a neighborhood of the orbit in case 2, right? Or in case 1, we know the same thing with curly C. So now, so each time we apply this map again, we're not going to get much further because this median operator is one Lipschitz, right? It was in the exercises, but if you haven't done it, it's one Lipschitz, right? So since little m is Lipschitz, whenever we apply these things finitely many times, we still stay in a bounded neighborhood of the orbit. So mr of O is going to be contained in the, say, R prime neighborhood of O slash same thing with CR. And that's it, right? Because now this is a subalgebra by Bowditch. This is convex. So, and well, it's clearly H invariant because what we've done is canonical. And since we're staying close to O was cocompact for H because it's an orbit pretty much by definition. X is locally finite because it has a geometric group action. So if we have an H cocompact set, we thicken it by a little bit, it stays H cocompact, right? And so that's what we wanted. Yeah, it's I'm not going to write it. Okay, so now we're ready to prove the theorem. And essentially, what is the trick here? The trick is that, so we're going to show that centralizers are always median cocompact by showing this. And this is actually, I'm going to only prove it in cube complexes, but the proof is the same. If you know about coarse median groups, what I'm going to show is that in any coarse median group, centralizers are coarse median subalgebras. So satisfy this. So, okay, so again, G acts on some cube complex properly and cocompactly. We fix a point, base point. We have a finitely generated subgroup generated by, let's say, A1, AN. And we call Z its centralizer in G. Right? So what is the goal? Right? Show that if you take a median of 3 points in the Z orbit of P, then this stays close. Okay, so maybe this I keep. Okay, so now, well, consider a point in this set. Actually, let's give it a name. So let's call it omega. So consider a point in there. Let's say X is a median of ZP, Z prime P, Z double prime P. Well, so we want to show that essentially this is still near the centralizer. So in some sense, this point still kind of commutes with H, right? So let's see what happens when we apply one of the AIs, right? So when we apply one of the generators of H, well, we can bring it inside the median, and then AI commutes with Z, right? So we can swap. And now, well, the median is Lipschitz, and this point AIP, well, it's not too far from P. I mean, right? So this is roughly the point we started with, right? X, and roughly meaning that the distance between the two is at most 3 times the distance between P and AIP. And we're basically done now, right? Because just call C the maximum distance where, I mean, there are only finitely many AIs, right? So what we've shown is that for every X in omega and for every I, the distance between AI X and X is at most C, right? And well, this just implies that X is in some neighborhood that depends on C of the given orbit of Z, right? So Z lies in some neighborhood depending on C of the Z orbit. Okay, so if this last spot is not immediately clear to you, I mean, the way you can do it is by just transferring the problem to the Cayley graph, right? So the cube complex is just going to be quasi-symmetric to the Cayley graph. So all we're saying here is that if, right? So if there is an element X in G such that this holds, right, then it lies close to Z. So in saying this is the same as saying that the norm of the conjugate most C, right? So you can look at the map that, well, goes from G to, well, n copies of G. And for every element X of G associates the conjugate of AI by X. Right? So this is a map. Let's call it alpha, right? And what we know is that, well, certainly alpha has finite image when you apply it to omega, or like this set of group elements that do this, because the image is contained in a product of balls. Right? So alpha of omega is finite. And what are fibers of omega? Well, a fiber of omega is just a right coset of Z, right? It's a right coset of things that commute with AI, with all the AI. So fibers of alpha are right cosets of Z, right? So what this is showing is that omega is contained in some finite union of right cosets of Z, which is just saying it's staying close to a copy of Z or that. And that's it. Any questions? Okay, then I have an even better surprise for you, which is that since it's Thursday afternoon and I'm done with the things I wanted to say, that's the end of everything.
For the example, I mean, I'm guessing you get the...
Which example? Oh yeah, you want to know what, I mean, the centralizer is just a copy of Z, right? And it's the diagonal copy of Z inside Z to the n. That's a median subalgebra. And end of the story. But yeah. Oh, because like whenever, like, as this gets bigger, and this bounds gets worse. So yeah. Although like in most